Okay. So, today we will discuss the Ellis rule and Telus theorem. We have seen already if the limit of the function f x when say x tends to say suppose a is our x tends to say c is say a and limit g x when x tends to c is say suppose b, then if b is not equal to 0, then one can find the limit of the f x by g x when x tends to c, and basically this is equal to the a by b. Okay. But if suppose in case a is also 0, b is also 0, if b is 0, a may be anything, then also we can discuss something, and it is shown that if the limit of the derivative exists, then this must be say 0, and in case if this b is 0 and a is less than 0, negative, minus infinity, and b is 0, a is positive, then limit will go to the plus infinity. Now, the case when a and b both are tending having the limit value with 0. So, when you consider the limit of the function f x over g x when x tends to c, it comes out to be 0 over 0 form, which is known as the indeterminate form. Indeterminate form. Why indeterminate? Because you cannot say the value of this is 1, or value is some finite number, or value does not exist. In fact, 0 over 0, it may exist, value the limit may exist, limit may not exist also, and like this. For example, if we take the function f x say alpha times of x and g x say x and choose the limit c as 0, then obviously limit of f x as x tends to 0 is 0, which is the limit of g x when x tends to 0. Both are coming to be 0. So, when you take the limit of f x over g x as x tends to 0, then in fact, this is coming to be, if you take the limit of f x over limit of g x, then it is basically coming to be 0 over 0 form. But if I substitute the value f x in g x, then the limit will come out to be alpha, because x will get cancelled and x is independent of any x. So, limit will come out to be alpha, a real number, where alpha is a real number. So, it means the limit of this 0 over f x by g x when it amounts to be the 0 over 0, then it may exist and may have a value real number, or sometimes may not exist also, that we will take some example where the limit does not exist in the case. Okay. Say for example, limit does not exist. Suppose I take another one, f x equal to x sin say 1 by x and g x is equal to x. So, if I take c equal to 0, then both the limits f x when x tends to 0 is 0, limit g x when x tends to 0 is also 0. But when you take the limit of f x by g x as x tends to 0, it is coming out to be the limit of sin 1 by x when x tends to 0, which does not exist. So, in the initial form it is 0 over 0 form, but basically the limit does not exist. So, that is why to evaluate such cases, to find the limit of f x by g x when it amounts to be 0 over 0, then we require some rules, and that is given by the L'Hospital's. Now, one more thing, here we are choosing the limit even if f of c is 0 or g of c is also 0, then in that case limit of f x by g x when x tends to c is also in the same form 0 over 0. It takes this form, which is also indeterminate form. So, if the function is defined at the point c, limiting point, and if it is coming to be 0 over 0, then the limit of f x over g x to calculate the limit becomes a problem, or even the limiting value is also coming 0 by 0, then it is also we cannot use any limit rules for the limits. That limit of the rational function is the limit of the numerator over limit of the denominator, which we cannot apply here. So, in such cases we require some concepts, and that is how to evaluate this limit of this ratio where it is coming to be 0 over 0 form, and that is given by the L'Hospital. So, before going to L'Hospital, there is one we will say the indeterminate forms. Is the 0 over 0 is the only indeterminate form? No, there are many cases which are considered as an indeterminate form. So, let me say the indeterminate forms. These forms are, first form is 0 over 0, infinity over infinity is also considered to be indeterminate form, 0 into infinity, that is if f x tends to 0, g x tends to infinity, then f x into g x, this limit will go to 0 into infinity form, or f x by g x if g x also. Then 0 to the power 0, if f x tends to 0, g x tends to 0, then limit of f x to the power g x, this, okay, when x tends to c. If it is coming to be 0 to the power 0, then it is also considered to be the indeterminate form. 1 to the power infinity will also be taken as indeterminate form, and infinity to the power 0 is indeterminate form, infinity minus infinity is also an indeterminate form. So, there are various types situation where we can say the limit the forms which you are getting is an indeterminate form. To evaluate this type we require certain tricks, okay, because just by substituting the value or taking the limit we cannot say the limit is correct, okay, or we cannot evaluate, which may be real number, which may be infinity or minus infinity also, and let f and g be differentiable, f and g be differentiable on the open interval a b, such that the derivative of g does not vanish anywhere inside this interval a b, that is non-zero for all x belongs to. Now, suppose that the limit of the function f x when x tends to a plus is 0, which is the same as limit g x when x tends to a plus, both are having the limiting value right hand limit exist and equal to value 0, let it be 1. Then the result says if this condition, if limit of f x over g x, f prime x over g prime x when x tends to a plus, if the limit of their ratio of their derivatives exist and is a real number L, then the limit of the f x by g x when x tends to a plus from the right hand side will also exist and will be having the same value as the limit of f prime over g prime is there when x tends to a plus. The second is if suppose L is infinity or minus infinity. So, if limit of this derivative f prime x over g prime x when a tends to a plus is suppose L, which is either in minus infinity or plus infinity only, then the limit of this f x over g x when x tends to a plus will also be minus infinity or plus infinity depending on L. Okay. So, this is what is known as the law. So, what this Ellis rule says is that if we assume the differentiability of the function, differentiability of the function, but not necessarily at the point A, then the behavior of the limit of f x by g x and the behavior of the limit of f prime x over g prime x will be the same. That is, the limiting behavior of f prime over g prime will be the same as the limiting behavior of f x by g x, whether L is finite or infinite or minus any real. Now, here second point which we also want to discuss, though I have taken the limit a plus, means the interval is this a b, and we are taking the limiting value from the right hand side, but the same result continue to hold good when we take the limit b minus or a minus, suppose it is completely defined, or limit exist. If the function has a limit at the point x equal to a, then we can replace a plus by a like this. So, if the limit of f prime over g prime at x tends to a is L, then the limit of f x over g x over x tends to a will also be L. So, in case limit f x as x tends to a exist and 0 and equal to the limit of g x when x tends to a, when f and g both are having the limit, I am not taking only the right hand limit, let us limit exist. Then if limit of this ratio f prime over g prime x when x tends to a is equal to a exist, then limit of their ratio will also exist and will be the same as L. It means the proof will remain the same whether we replace a plus by a or a plus by a minus, provided the limits are there. If the left hand limit exists, we use this. If the limit exists, we use this. If the left hand limit exists, right hand, then this left hand limit exists, then a minus, and like this. But the result continue to hold good. So, we will establish this proof when the right hand limit exists. Okay? And for others cases, the proof is the same. So, let us see the proof. Now, let us take an alpha beta lying between a and b. Okay? Now, since the function g, which is given to be differentiable over a b, since g is given differentiable over a b and g prime x is not equal to 0. So, this automatically implies the value of g beta will be different from g alpha. Why? The reason is otherwise by Rolle's theorem, if a function g which is continuous over the closed interval a alpha beta, differentiable over the open interval alpha beta, g is given differentiable over alpha beta, and if the end point alpha and beta the values are same, then there will exist a point c lying between alpha and beta such that that is a and b, such that derivative of g at the point c must be 0, which contradicts our assumption that g prime x never vanishes for any x belong to the interval a b. So, always this result will be true, that g alpha is 0. Okay? Now, take the interval alpha beta, apply Cauchy mean value theorem for the function f and g over the interval alpha beta. So, what the mean value theorem says, if f and g both are continuous over the closed interval alpha beta, differentiable on the open interval alpha beta, then f of b minus f alpha divided by g beta minus g alpha is the value of the f prime set c or f prime u divided by g prime u for some u in lying between alpha and beta. So, by mean value theorem, there exists an u belongs to alpha beta such that f beta minus f alpha g beta minus g alpha is the derivative this thing for some u. Okay. Let it be 2. Clear? This is by deal. Now, let us take the case 1, say A. What A? It is given limit of this is given limit of f prime over g prime when x tends to A from the right hand side is L. This is given. So, given limit x tends to A plus f prime over g prime derivatives is L. Okay. So, given. So, let us take so if L is given, that is if L is known, which is in R, and let epsilon be, and if epsilon greater than 0 be given as some positive number. Now, limiting value of this is L. It means when the point A close to some interval, say AC I take. So, whatever the point x in between this, the limiting value of this prime is L, means difference is very, very small. So, this lies between L minus epsilon and L plus epsilon. So, we can say there exists a C belonging to the interval A B such that f prime x over g prime x lies between L minus epsilon and L plus epsilon for all u. Let us be this u. So, let us take the all u. Okay. All u. For all u belongs to the interval A C. Okay. We can find the neighborhood of right neighborhood of A, where if we take any point in that right neighborhood of A, this condition will be satisfied. Okay. But f prime u over g prime u we have already find out from there, is it not? So, from 2 we have discussed this, from 2 f prime over g prime is this. So, substitute this value. So, use 2, hence from 2 we can say L minus epsilon is less than f beta minus f alpha over g beta minus g alpha, which is less than L plus epsilon for A less than alpha less than beta less than equal to C. Now, take the limit, take limit as alpha tends to A plus, because A plus this limit will be 0, is it not? So, this limit will be 0, this will be 0. So, what we get is, so we get L minus epsilon is less than equal to, when you take the limiting equal to sign may also come. So, this is less than equal to epsilon, and this is true for all beta belonging to the interval A C. Therefore, this shows the limit of f x by g x when x tends to, because this limit, is it not, when this one is there. So, limit beta tends to A. So, when you take x in place of beta I am taking x. So, x tends to A plus is also L, because here let beta approach to A from the positive side, that is equivalent to say that x approach to A plus, where x belongs to this interval. So, this shows this. Okay. The second case, when L is plus infinity, L is plus infinity, and if m be choose greater than 0 is given, because the limit is giving to be L, which is infinity. So, what do you mean by this? It means that there exists a C belongs to A B, because this is given, yeah, this is given, this is suppose infinity. It means when point is closer to A in the right neighborhood of A, then this limit can, this value can exceed any positive number. So, I am taking m to be greater than 0, then a number u can be obtained. There exists C such that for all u this condition is satisfied, is greater than m for all u belongs to AC. Okay. And but since epsilon is arbitrary number, this then from here this implies f of b, this implies again substitute 2. So, f of beta minus f of alpha divided by g of beta minus g of alpha is greater than equal to what? M is greater than m, strictly greater than m for all alpha and beta lying between this bond, okay, in the right neighborhood of A. So, take the limit as alpha tends to A plus, and immediately we get the f beta over g beta is greater than equal to m for all betas belonging to AC. And this shows, since m is greater than 0 is arbitrary large number. So, limit of this f beta over g beta when beta tends to A plus will be infinity, and that is full. The other cases follows in a similarly we can show for other cases results here. Okay. So, let us take the other determinant forms, other indeterminate forms. So, case by case let us take, say first case is infinity minus infinity. I will give by example, seeing that a case of this where infinity minus infinity type. Okay. So, say for example, let I is the interval 0 pi by 2 and consider the limit of this as x tends to 0 plus 1 by x minus 1 by sin x. So, when you take x tends to 0, it is of the form infinity minus infinity. So, how to solve find out the value? What we do is we take the LCM. So, limit x tends to 0 plus, this is the same as x sin x minus sin x minus x. Now, it reduces, this is infinity minus infinity, now it is 0 by 0. So, apply the Hospital's. So, when you apply the Hospital's rule, differentiate the numerator and then differentiate the denominator. So, we get sin x plus x cos x and take the limit as x tends to 0 plus. If this limit exists, then limit of this will be the same as this. Now, x tends to 0, it is 0, again 0. So, it is again 0 over 0, so on. So, further apply the Hospital's rule. So, when you take the, because all the f x and g x satisfy the conditions of L'Hospital's. So, we get x tends to 0 plus cosine x is minus sin x divided by say cosine x and then x. So, again cosine x then minus x sin x. So, when you take the limit of this, what you get is x tends to 0. So, that comes out to be now 0 over 2. So, this is 0, answer is this. Okay. Second case is say 0 into infinity type. Suppose I want to take the limit of this x tends to 0 plus x of ln x. So, when x tends to 0, it is 0 into minus infinity, that is 0 into infinity type. So, how to get it? This one is, what we do is we put it this in the form of 0 over 0 or infinity over infinity. So, if I take the ln x divided by 1 by x as x tends to 0 plus, then it is infinity by infinity type. Okay. Of course, minus infinity makes no difference. Then apply the L'Hospital's rule now. So, once you apply the L'Hospital's rule 1 by x and here denominator we get the minus 1 by x square as x tends to 0 and then when it comes up you get the value 0. So, it is coming to be 0. Third case, when it is of the form say 1 to the power 0. 1 to the power 0. For example, suppose I take the limit of this 1 plus 1 by x as x tends to infinity power x, 1 to the power infinity, sorry, x tends to infinity, okay, 1 to the power infinity. So, it is when x tends to infinity, this is 1, this is infinity. So, infinity to the power infinity. So, what we do is we consider this L, limit L, take the log. So, when you take the log, it is comes out, because limit is a continuous function, log will go inside and we get log 1 plus 1 by x, and x tends to infinity. So, basically when x tends to infinity, is infinity into 0 type. So, this can be put it again either 0 over 0 or infinity over infinity type. So, we can put it this as 1 plus 1 by x divided by 1 by x limit x tends to infinity, that is infinity over infinity type. And then apply now Ellis-Peters rule. So, if we apply the Ellis-Peters rule, what we get, differentiate the numerator. Numerator differentiation will give 1 over 1 plus 1 by x, and then derivative of this will be minus 1 by x square, and then minus 1 by x square. So, and then take the limit as x tends to infinity. So, basically this limit comes out to be 1. So, since log of L is 1, is it not? Log of L is 1, therefore, so log of L is 1, therefore, anti-log of this will e to the power 1, that is e. So, answer is basically e. Then next case is for when it is of the form say 0 into infinity 0 into 0 type, 0 power 0 type. So, for example, if we take the limit x to the power x when x tends to 0 plus. So, it is 0 to the power 0. Again in this case take the L log, and when you take log, this problem is reduced to the case when it is 0 into infinity type. So, just like a previous one, we can take it log x by x as x tends to 0 plus, then apply it is infinity 1 by x. So, infinity over infinity. Now, apply the Ellis-Peters rule. So, when you apply the Ellis-Peters rule, differentiate the numerator and denominator separately and take the limit when x tends to 0 plus, and this limit will come out to be what? 0. So, the L will come out to be e to the power 0, that is one answer. Then another case 5th, which is of the form say 1 to the power say again what form left now, infinity minus infinity we have taken, and then let us take another case is limit of this x tends to 0, 0 into minus infinity x log x, that we have already considered. So, I think this is all forms we have discussed, is it not? So, let us see. Okay. So, we can say another form infinity, and let us take one more example, then what we want. Suppose I take 0, say 1 minus x, x tends to 0, okay, into say 1 to the power infinity. So, let us take the 10x, no, cot x, and x tends to 0. So, what this is the 1 to the power infinity. Okay. So, what how will you do it? Take L and then log L. So, log L will be equal to what? Cot x into log 1 minus x, and x tends to 0 plus. So, cot 0 is infinity, this is 0. So, 0 into infinity, then again you can take log 1 minus x divided by 10x, and x tends to 0 plus. So, it is 0 over 0, apply Ellis-Peters rule, and we get from here is differentiate numerator, differentiate denominator, take the limit when this goes to 0. So, when you take the 0, upper limit comes out to be 1 and this is sec is also 1, the limit will be 1. So, L will be equal to e to the power 1, answer will be this. So, that is what is shown. So, it is almost we have completed this one. Now, let us come to the Telus theorem. The Telus theorem, it is an extension of the mean value theorem. Mean value theorem, we give the relation between the functional value and its first derivative, whether it is a Lagrange's mean value theorem, f b minus f a or b minus a derivative of the function, or maybe the Cauchy mean value theorem, where the two functions f and g are there, and then we get the relation between f, g and their derivatives. Telus theorem is an extension of the mean value theorem, where we have a relation between f and its higher order derivatives, and it is basically used to approximate the functions with the help of the first few terms of the Taylor series or Taylor theorem. What this theorem says is, let n belongs to capital N, okay, and let I is the closed interval a b, and let f is a mapping from I to R be such that f and its higher order derivatives say up to order n, f prime, f double prime up to f n, the nth order derivatives up to R continuous on the interval I, and that the n plus 1th derivative exists on the open interval a b. Now, if if x naught is a point in the interval I, then for any x belongs to I, there exists a point C between x and x naught, such that f x can be expressed as f x naught plus f prime x naught into x minus x naught plus f double prime x naught over factorial 2 x minus x naught whole square and so on, and then plus f n at the point x naught divided by factorial n x minus x naught to the power n plus the remainder terms R n x, where R n x is given by f n plus 1 c over factorial n plus 1 into x minus x naught to the power n plus 1, and this is known as the Lagrange's form of the remainder. So, the function f is such which is differentiable and continuous up to say n plus 1th order time, and n plus 1th order derivative exists in the neighborhood of the point x naught, then there exists in the open interval a b of course, and the neighborhood of the x naught. Then there exists a point C where the expansion of the function f x can be written in the form of the series, where the first n terms of the series is the polynomials of degree n, and this term is called the remainder term, and it is known as the Lagrange's form of the remainder. Now, in case if the remainder R n goes to 0, then this same expansion is known as the Taylor series expansion for the function f x. Okay. So, we will discuss it next time, the proof of this. Thank you very much.